Friends, when we are purchasing laboratory reagents such as H2SO4, HCl, HNO3, acetic acid or ammonia, then such reagents are not having mention of concentration on their bottles. So how we can determine concentration of such laboratory reagents? Hi, this is Dr. Taide and I welcome you all to the educational channel of our college Rajarshi Shahu Mahavidyalaya Latur. Let's have an exploration on the laboratory reagent H2SO4. Today's agenda points are introduction to the laboratory reagent H2SO4. We are going to explore the properties of H2SO4, both physical and chemical properties we will discuss. Then we will go for the determination of concentration of laboratory reagent. After determination of this concentration of laboratory reagent, we can go for the preparation of dilute or working solutions of that laboratory reagent. Later on, we will discuss direct preparation of its dilute solution without determining concentration of original laboratory reagent. We will conclude at the last and go for the key takeaways. Let's have an overview of H2SO4. H2SO4 is known as sulfuric acid. This H2SO4 is the molecular formula of sulfuric acid. H2SO4 is also known as oil of vitriol. It is highly corrosive, strong mineral acid. You can also say that it is inorganic acid because it is not having carbon, which is a absolute requirement of organic compound. So it is not organic acid, it is inorganic acid. Also I am saying it is acid because it is able to donate hydrogen ions, and according to the Bronsted-Lowry theory, we can say that it is acid. It can dissociate up to 100% in water. It is having wide range of application in various chemical processes. Let's see importance of concentration determination. Concentration determination is very crucial factor when we are going for any reaction for ensuring the effectiveness of the reaction as well as safety of the chemical reaction. We should determine the accurate concentration of the laboratory reagent in compliance with regulatory standards. Let's have a look at applications in various industries. So H2SO4 is used in various industries. We can see that this HCl, HNO3 are also prepared from H2SO4 only. If you are reacting NaCl with H2SO4, it is leading to formation of HCl. If you are reacting sodium nitrate or potassium nitrate with H2SO4, then it will lead to formation of nitric acid. This H2SO4 is used in many industries such as dye industries, polymer industries, petroleum industries, in fertilizer industries. So we should determine the concentration of H2SO4 very crucially. It is having a vital role in operational efficiency in case of the industries. Now we will see the physical and chemical properties of H2SO4. H2SO4 is colorless, odorless. It is not having any odor as such, and it is highly viscous liquid. It is hygroscopic in nature, means it catches moisture from the atmosphere, and it is having high boiling point. You can see that instead of the oil bath for determining the boiling point, you can use H2SO4 bath. But proper precautions you have to take. I have mentioned that it is highly corrosive in nature, so you have to take proper precautions so that H2SO4 should not bump, and if it is leading to serious injuries to you. I have already mentioned it can dissociate up to 100% in water, so it is having highly acidic properties. It is very strong acidic in nature. Reactivity and safety considerations. Sulfuric acid is highly reactive. It is capable of causing severe burns, and it is releasing heat upon contact with water, so necessitating rigorous safety protocols. My friends, you have to always add acid into water. You don't have to add water into acid. Why it is so? Because acid is having higher density. As mentioned here, when acid is dissolved in water, it is exothermic reaction. A heat is liberated, a large amount of heat is liberated. Density of acid is higher when you are adding acid into water slowly with stirring. Then you can see that the acid is going at the bottom. It is not leading to any bumping, and so there is no question of having any injury to you. So always add acid into water with slow stirring. A slow addition you have to go for. Okay, let it be. So you have to take proper precautions in case of sulfuric acid. There are MSDS, that is material safety data sheets. Nowadays they are called as safety data sheets, SDS. So you have to look for the symbols and their meanings given in the MSDS so that you can avoid the health hazards of H2SO4. Now we will see the role in chemical processes. I have told you that it is having very strong acidic properties. It plays critical role in dehydration, oxidation and sulfonation reactions, making it indispensable in chemical synthesis. My friends, you can see that our general observation is that if H2SO4 is coming in contact with our skin, then our skin is becoming yellowing. There is a yellowing of skin. Also, you can see that the skin is becoming dry. Why is it so? The skin is becoming yellow because that H2SO4 is oxidizing our skin. Then you can see that the skin is becoming dry because H2SO4 is having dehydrating properties. These roles it is playing in chemical reactions also. So it is having indispensable. It is indispensable to use H2SO4 safely in chemical synthesis. Let's have a peep at molecular weight calculation of H2SO4. So you can see that the approximate molecular weight of H2SO4 is 98 gram per mole, or you can say that it is 98 U. That U is representing symbol of atomic mass unit. This is calculated by adding atomic masses of the atoms which are constituting H2SO4, that are the hydrogen. 2 hydrogens are there, 1 sulfur is there, and you can see that 4 oxygen atoms are there. So 2 into 1, here roughly 1 is taken, that is the atomic mass of hydrogen. 32 is taken, that is the atomic mass of sulfur. Then for oxygen the atomic mass is 16. It is multiplied by 4 as there are 4 oxygen atoms here. If we are taking accurately, then you can see that hydrogen is having atomic mass that is 1.0078. I have rounded off it to 1.008 U, that is atomic mass unit. Why I have taken this? If you are taking these correct figures, then we can calculate the exact molecular weight of H2SO4. Rather than taking this rough figure 1, I will suggest that always take this atomic mass for hydrogen. For sulfur, the atomic mass is 32.06 unit atomic mass unit, and for oxygen it is rather than 15.999, I have taken 16, that is the atomic mass of our oxygen. So if you are multiplying these atomic masses with the number of atoms, then we can come to know about molecular weight, and you can see that it is 98.078 atomic mass unit I have calculated. And if you round it off, then after rounding off it is 98.08 atomic mass unit. So this is often expressed in grams per mole, or in case of in some cases it is mentioned as 98 atomic mass unit. Okay, now let's have a look at molarity calculation of H2SO4, or molarity determination of H2SO4. You can see that here I have shown a bottle. In the red circle I have shown sulfuric acid, and its percentage purity is given, that is 98%. You can see that the percentage purity is also called as assay, and it is the percent weight by weight, you can say. So this percent weight by weight is same as assay, or same as percentage purity of that H2SO4. It is generally ranging between 96 to 98%. In case of the fuming H2SO4, it can also be 99% also. Okay, so 96 to 98% percentage weight by weight is there, assay is there, or percentage purity is there, you can say. And my friends, the density is around 1.84 gram per ml. This is particular value at 25 degrees Celsius. The temperature may change the density. You can see that with this green arrow I have shown the molecular weight of H2SO4, which is there on the bottle. Molecular weight of H2SO4 is 98.08 gram per mole, as we have calculated. Just you should have idea about the molecular weight calculation. That's why I have made mention of that calculation. Otherwise you can directly jot it down from the bottle. The molecular weight is given, that is 98.08 grams per mole. Here some figures are shown, they are not visible, but amongst these figures this percentage purity or assay is given. Along with it many parameters are given, but we have to focus on assay, that is how much it is given in front also. And you can see that the density is also mentioned here on these parameters. So density is 1.84 gram per ml at 25 degrees Celsius. My friends, this density may vary. How it can vary, we will see. For instance, I have taken 20 degrees Celsius and 25 degrees Celsius. So for 100% pure sulfuric acid, the density is ranging between 1.83 at or 1.83 to 1.84 gram per ml. This density is expressed as specific gravity. You can see that density is having unit grams per ml or grams per centimeter cube, but specific gravity is unitless. I would like to mention here, specific gravity is unitless because it is a ratio of that H2SO4 to the density of the water. It is a ratio of two densities. The specific gravity is unitless. Also, the percent weight by weight, as it is a ratio, you can see that it is a ratio of mass to mass. It is also not having unit, it is also unitless. This, in the earlier formula we have seen, the 10 is there. So what is this 10? This 10 is a conversion factor to adjust the units. This is coming from the 1000 ml, that is equal to 1 liter, and percent. When we are dealing with the calculation, then that 1000 and 100, after cancellation we are getting 10. That's why it is a conversion factor to adjust the units. And you can see that the molecular weight is in grams per ml. The molecular weight I have taken in grams per ml here. Okay. Now, understanding the molarity computation of laboratory reagent H2SO4, this formula we have already seen in the earlier slide. You can see that specific gravity into percent weight by weight into 10 divided by molecular weight. So we will put the values. 1.84 is the specific value, specific gravity value. It is not having any unit, my friends. And for instance, we have taken here 96% pure H2SO4. The percentage purity or assay of H2SO4 is 96% we have taken into 10, that is the conversion factor. And the molecular weight of H2SO4 we have taken, that is 98.08 grams per mole. So when we are computing this value, you can see that we are coming to the molarity of H2SO4, and the molarity we have calculated is 18 molar, that is 18 moles per liter. You can convert it to normality also. This molarity and normality is having this relation shown. Normality is equal to molarity into 2. Here you can say that normality is equal to molarity into basicity. In case of H2SO4, the basicity is 2 because it is a dibasic acid. It can donate 2 protons. So according to the Lowry-Bronsted or Bronsted-Lowry theory of acid base, it is acid, and as it is donating 2 protons, it is dibasic acid, we have to say. Okay, so we have multiplied this molarity of H2SO4 by this 2, that is the dibasic acid is having basicity 2, so the normality is 36 normal. It means that when H2SO4 is 18 molar, it is 36 normal. Okay, we will have a deeper insight to the molarity computation of the laboratory reagent H2SO4. The same things we have taken here, but how it comes, that I have elaborated. You can see that the density is 1.84 gram per ml, and suppose the bottle is having the label of assay or percentage purity of 96%. Then what is the molarity of the acid sample? So molarity of H2SO4 is equal to weight of H2SO4 in 1 liter solution divided by molecular weight of H2SO4. So this weight of given H2SO4 per liter is equal to strength into density into 1000. Okay, so this 1000 is for 1 liter because it is 1 liter converted into ml, that is 1000 ml. Now the strength is, we have seen that it is 96% pure H2SO4 we have considered here. That's why 96 divided by 100 I have taken here. Then density is 1, actually we have taken specific gravity, that is 1.84 into 1000 is equal to this much is the value, and this value we have divided again by the molecular weight. By putting into this formula, we are getting 18 molar H2SO4. So this is the basic formula which we have directly taken there. Okay, so there we have mentioned it as assay or percentage purity, or we have mentioned it as percent weight by weight. The same thing is there. Here it is mentioned as strength. Okay, so you can recall any one. You just can take here percentage purity into specific gravity into 1000, and you can simplify it. Okay my friends, we will move to next slide. In the next slide we will see how we can prepare the dilute solution or working solution from this H2SO4. Many times we are having H2SO4 which is 18 molar, and we have to prepare 0.0001 molar H2SO4. So by this formula it is not possible. Why? Because very small volume is there in case of very dilute solutions of H2SO4. So what you have to do, you have to go for stock solution preparation. If we are having 18 molar H2SO4 as we have computed from the specific gravity and percentage purity details which are printed on the bottle, you can go for stock solution preparation. You can go for 6 molar or some 4 molar H2SO4 preparation, and after preparing this stock solution you can go for further dilution by the same formula. Okay, suppose I have taken 18 molar H2SO4 which is the original laboratory reagent, which is concentrated one, and we have to dilute it to 6 molar H2SO4. So molarity of concentrated H2SO4 into volume required of concentrated H2SO4 is equal to molarity of dilute solution of H2SO4 into volume of diluted solution. This we are going to decide how much we need as per our experiment we have to plan. If you are requiring only 100 ml, you can put here 100 ml. Okay, why to waste the chemicals? They are ultimately going to the environment and affecting us, affecting the flora and fauna. That's why we have to avoid the overuse or unnecessary use of the chemicals, my friend. Protect our environment. Okay, let it be. So by this formula we can determine the volume of H2SO4 required. At one side we have taken parameters of concentrated H2SO4, on the another side we have taken parameters of dilute H2SO4. The required concentration we have mentioned here, that we are going to prepare 6 molar H2SO4. After computing we can calculate that V of concentrated H2SO4, volume of concentrated H2SO4 we have to take, that is 333 ml approx. This volume we have to dissolve in a small water volume, and after dissolving into small water volume, as I have mentioned earlier, drop by drop you have to add this, or slowly with stirring you have to add this 333 ml H2SO4 into some 500 ml water, and then you can go for dilution of that volume to 1000 ml using the standard flask. Okay, that is the basic laboratory technique. So in case if you require very dilute solution, this is the original solution, original laboratory reagent 18 molar, then you have to go for a stock solution 6 molar, then you have to take 6 molar as concentrated, again go for preparation of some dilute solution, that is 0.1 molar or another thing. Because in this case if you are trying to prepare directly the required concentration from such higher concentrated solution, it will lead to very small volume and it may involve error. We don't have to introduce error in our experiment or in our analysis. So first, from this original laboratory reagent solution we have to go for preparation of stock solution such as 6 molar for example, and from 6 molar you can prepare 0.1 molar H2SO4, that is your working solution. So in this way, by double dilution you can prepare the required laboratory reagent. Now we will understand, without determining the concentration, how we can prepare the requisite solution of a particular concentration. So same example I have taken, that we are going to prepare here 6 molar H2SO4. So my friends, you can see that volume of H2SO4 for 1 liter solution is equal to whatever answer will be there, that will be in ml, and it is equal to 100 into required concentration into molecular weight divided by specific gravity into percentage weight by weight. My friends, we know that we have taken here that we have to prepare 6 molar H2SO4. So we will compute the values. Volume of H2SO4 for 1 liter solution in ml, 100 into 100 is taken for percentage, again 100 into required concentration is 6 molar in this example into molecular weight of H2SO4 we have already calculated, it is 98.08 divided by specific gravity. We know that specific gravity is not having any unit. I am again reinforcing it, highlighting it. So we have taken the value, that is 1.84 into 96, that is percent weight by weight. After computing we are getting the same volume. This volume you have to take and you just simply dilute it to 1000 ml, so that you will get again your required concentration solution. Let us come to conclusion and key takeaways. Explore MSDS, material safety data sheets, or SDS safety data sheets first, because you have to take care of yourself first. Proper precautions we have to take. It is flammable or not, it is causing any cancer or not, it is cancerous or not, it is radioactive or not. These all symbols are given in the MSGS, and you have to take proper precautions accordingly. Get familiar with the safety symbols. You should know that. The symbols are also printed on the bottles, so you should know that which symbol is representing which health hazard. The concentration of laboratory reagent is not directly written on the bottle, and it is need to be computed as discussed by me in this presentation. So using the formulae I have depicted in this presentation, you can determine the concentration of the laboratory reagent. For acids, the density of acid is more, then you have to add acid with slow stirring into water. Never add water into acid. It is highly exothermic reaction, so you have to take proper precautions. Never add water in acid, as it can lead to bumping and can cause severe damage to the analyst. This is the small Google form quiz I have mentioned here. You can go for the link, or you can just simply scan the QR code. Kindly attempt the quiz so that you can be benefited. You can test your knowledge. For further reading, I suggest this references learning or reading. Thank you very much for your patience learning. I hope you have understood it. I'm also thankful to visionary principal of our college, Principal Dr. Mahadev Gawane, for giving me this opportunity to record the video and present in front of you peoples. Best regards to you.